to do on. Okay, good afternoon. Oh, some echoing. Okay, so I think we can continue today plastic, and then after plastic, because the plastic part I was supposed to include before exam 2 because of a hurricane, right? So then I had some kind of usually I put this plastic some sort of questions practice in support material. I have to shift. So I'm going to make like as a quiz entering. So it's not going to relate it to be point, but you can practice until the final exam. So I just started and I have not finished it yet, but maybe by like this evening, because I have a huge all really non-stop meetings till like 6:30 today. I mean, of course, office hours are yours. Of course, you can come. But anyway, I don't know how much I can complete. But by this evening, sure, I will complete. So, I think we can, or you can do as a quiz, plastic. No? So, let's continue. So, this is later. We will, because today I want to do plastics and then also, machining. That's going to be chapter 7, which probably is easier for you because you did the DML, right? Did you? Sorry. Yeah, students, international students who came from outside, it's different. I mean, DML lab is like UF's, undergraduate student has some sort of lab. So they can learn machining, turning, milling, and drilling, So then, compared to like a plastic forming or others, they actually experience. So I think easier to, understand, So I think this is, today's page, because I know usually I start a new page, but we are, we wrote this one, so we watch video, So that's, so let's say compression molding. I think today start from, here, bless you, and then today is like, what, 30s already? Okay, so let's start. So last time, we talked about plastic, and then, like thermoplastic, injection molding, right? Because they can be kind of warm up and they can be really, thin, like soft, and then flow. But like thermoset, because of they heat up, then it's not like a softening, right? Because of the heat, actually make it harden, right? So then, how can we use? Because it's not bad or good; it's just a characteristics. So these kind of polymer, like a most I put compression molding. So that's, figure actually 6.15. So that's a, textbook. So let's take a look at this, textbook page, this one. So in this case, instead of flowing, and then you have, kind of dye or mold. And then mold is going to heat up, And then you put some, in this case, preform, some like whatever polymer, thermoset. And then, for this, the pressure, so they can make, in this case, this kind of shape. So that's a big difference. Some, plastic, you have like, like big machine, and you just kind of feed and then put into the pressing, but it's not so flowable. That's why, we have this kind of, mold and heat up, and then, that's, compression, right? Compression molding. And then transfer molding. So that's going to be next page, figure 616. So this one is slightly, flowable, slightly. So this is figure 616, and then, similar to, previously, you have to have some cavity, right? I mean, even impression, sorry, not impression. Like injection molding, they have, mold too. So this time, here, this, can you see the cavity? So you are going to fill this kind of, this black one, dark one, that's thermoset preformed. It's a previous one, So like you are kind of sheets, right? And then you put it, and then you warm up, like heated mold. You warm up, and then basically you press like this, and then slightly pushed out. So that's, transfer molding. Straightforward, right? That's so that's anyway, thermoset polymer can be treated, and there are many examples. Go thermoset compression molding. So my experience, so I don't have picture. So like knee prosthesis, when we did research, and then like knee, right? That's a metal, and we did polish. But usually, knee and the cartridge. So knee is going to be like that, So this cartridge side, this polymer, was made like with this, compression molding, the polymer. And then, this knee side, I hope you don't need it, You have to be, make very smooth surface. Smooth means like, can you guess how smooth it should be? Like knee side, Because otherwise this is polymer, right? This is metal, right? Even if okay, make good surface, but if this has a rough surface, you're scribing and scratching, right? Then debris is going to make inflammation because it's in the body, like leg, right? So this, can you guess how smooth it should be? Because each company has a different, roughness. RA or what, how many? RA, micron or nano? Nano. So like 2,000 nano, so 2 micron. It's guess. Don't worry, Don't worry. And every company has a different, And then if you need, you don't have time to check, right? Because it's surgery, right? So that's usually what I did when I did, like less than 5 nano, 2 nano. That's the level. But it's still not enough, So, but anyway, that kind of, smoothness, but this, cartridge, this side, is usually made using this, and then this polymer, they don't want to get softened, right? Because otherwise, this is going to get warm, and they have an issue. That's I think, easily I can think, what else, I have to think. But so that's, compression molding. And then casting is a cast. I don't think we need to explain. It's just a cast, like a, just to cast, right? And then thermoforming. Maybe this one, can you guess what's thermoforming? Like, plastic cup, like drink. Maybe, thermoforming, like here, like film or sheet, right? And then thermoplastic material. So you have a sheet, and then you have a mold, and then you cut, and then you form. So, but again, mold and vacuum. So there's a video. So I think we can show video first, and then you will see, something like that. But this is really mass production, right? Cup, plastic cup. That, last time I think, today, yeah, she has again, right? Excellent, right? So, right? Usually you kind of, like a lot, right? And then you can buy in a Publix or somewhere, right? Yeah. Are you going to pay $100? No, right? And then are you going to reuse many times wash? No, right? One time, right? Probably for the outside, right? So it has to be cheap, right? So then how we can make it? That's this process. So let's take a look, And then we watch together, right? And then you have this information. For example, Lego. Did you watch Lego video? Yes, please watch, the video. It's going to help, not just understanding here. Like then you will appreciate how the products were made. You will be engineer or researcher, right? After you graduate, right? And I know you make something, you're not asking somebody to tell you, oh, thank you so much, right? You're not going to do that. But if somebody appreciates your product, you feel really, really much, not just better or worse. It's rewarding, Then I feel like, oh, I'm good. I'm proud of being, engineer or something, That should be in your somewhere, So anyway, this one, thermoforming. And I don't remember which one is the best, but let's go first one. I think I opened it. Okay, wait.
From the Atlantic
because then we don't have to watch,
Ocean to the Gulf of Mexico. From the
Thermoforming technology involves obtaining a desired shape by
Don't
heating
worry,
and
I'm going to
forming a
make-
plastic
I will
film
do
or
again.
plastic cut.
Okay, I will do again one more time.
Involves
Okay.
obtaining a desired shape by heating and forming a plastic film or plastic cut sheets. It's an interesting but not easy process, and it requires a lot of
Then
experience.
This mold has a hole and
Thanks to this-
vacuuming. You know?
A lot of packaging on store shelves. Today, we will see how the thermoforming process works. For this purpose, we are visiting the production facilities of the family company Poly. First, we are visiting the product design department, because this is where every project begins. Here, all projects of packaging that have to be implemented in production are born. After accepting the packaging design, it's time to prepare the design of tooling which will be used to produce the item. The tooling is created in the CNC department on numerically controlled machines. The complete tool consists of the forming station, including mold, plug assist and cooling system, as well as cutting station and stacking station. However, the main part of the tooling is where the shape of the product is created. In this part, vacuum holes of 0.4 mm diameter are drilled. Through them, the thermoplastic material is sucked into the mold surface. The holes are so small that they are not visible on the packaging. With the finished tool ready, production can begin. First, we will see how small packaging for the food industry is produced. The film is unrolled and then heated at the first two stations. The temperature of about 200 degrees Celsius makes the film malleable. Then it goes to the forming station. The material is initially stretched and shaped with pressure and vacuum. The material cools down and thus the shape of the detail is preserved. In the next station, individual products are cut out with the die cut. Next, they are picked up and placed by a robot. The moment of forming of the product is clearly visible in machines which produce large-sized thermoformed elements. The product is made of polycarbonate cut sheet of about 8 mm thickness. The raw material has high transparency, just like glass. The cut sheet is heated on both sides. Then, with a blow, the flexible material is vacuum sucked into the mold.
Beautiful, right?
On a cold form, the material stabilizes. Cooling takes about 180 seconds.
Okay, so I'm going to stop here. Okay, because the hole, if its hole is big, your product can show this kind of dip, right? You don't want to have that, right? Because if you put some food or drink, and then, maybe it's gonna stuck there, right? So that's not good. So, this is like kind of, one example. Wow, right? That's really wow.
After collection,
the triangular, that's a shape, They are mold shape, I'm not talking about that. Okay. So that's, and then, I am not going to show everything, but I think this. Sorry, this doesn't work. Okay. I don't know. Just arrow and then so this is like a cup, how, so just a little bit, and then you can watch at home. That's why you can buy the stack of cup in what, $10 or something like that. So anyway, this process, actually you see a lot of product, but you have never thought how it's made and why it can be so cheap. So then now you learn, right? So next time you go to, like Publix, just take a look. You don't have to buy it, but just take a look. I think that's, about it, about plastic like processing, the major process. And then if you look at the figure, 6.44, this also, kind of explains step by step, so how, this thermoforming works, dye and sheet comes, and then form, and then, vacuum, So then I think, also reading this page maybe helps your understanding. Any questions? It's good? Again, I will prepare, quiz. I mean, I'm doing that. So just wait, and then I think you can, use that as a reviewing material. Okay. Okay. So now, we can move on to chapter 7. So let's, go to chapter 7. Hey. Where is my? Okay. So new page. Yeah. So chapter 7 is, machining. So I am also, my expertise is like, machining. I wanted to do forming, but I did machining. And then research-wise, I wanted to do cutting, but I did abrasive polishing. So now I'm free, right? I'm not a student, right? So after I finished PhD, I did a cutting research. And then now recently, right, about like 5-6 years ago, before COVID, I started, forming research. So now, that's why I can teach, and also, I can talk, because I know I do, I do research, so I can do more than probably, some section more than textbook. So cutting-wise, right? I'm doing since 1990. How many years I'm doing research, So I should not use textbook. I should just like, give lecture, but it's not. So I just follow, this textbook, but we will learn together. But before we go to textbook, I always tell very fundamental, which usually, for some reason, this country, they don't teach. So that's why I want to share the information, because you need to know. You really need to know. So then chapter, I will write still chapter 7, because the context, or material is under this one, cutting technology. This is a fun part. So first, they will study single point, tool operation, but single point before that, turning, that's single point, right? Turning, you use lace, right? So then also milling, that's also cutting, right? Even drilling is cutting, but turning, milling, you use cutter, right? So cutter can be, like a drill bit. Cutter can be like, just a milling tool. Can be like, lace-wise, like a bit, or even chips, right? Throwaway kind of, chips, like triangular, or even, diamond. You can just, rotate. You can use multi-corners or something like that, right? So that's the tool-wise, even like a cutter, let's say. Cutter you use. Then, after you machine, sometimes you want to have smoother surface. Then you will go next to abrasive, but grinding, right? Next process you usually use. Grinding, and then grinding case. What is the cutter or like equivalent is a grinding stone, right? Or grinding wheel, right? So grinding stone, probably you have at home, like you have a knife, and then you kind of sharpen. This is the stone. Do you sharpen your knife? Okay, good. Somebody said no. Okay, you should, right? Otherwise, when you cut something, tomato, right? Right? Tomato is soft, right? But maybe potato is fine. You can put the force. But if you have really nice, good edge, you don't have to put any force. Just gravity can cut. That's how it should work. So if you cut your vegetable, You have to put your force. You gotta check. And then grinding stone is the abrasive, right? And then you have abrasive bonded, right? And then you have air pocket. Because otherwise, it's going to be loading. But just to give you the idea, if you don't have grinding stone, and then you have like, okay, this is a coffee cup or something, and then backside, right? Something like that, right? If I look at from the bottom, right? So then this section, usually rough surface, right? This is a porcelain, right? So then if you don't have a grinding stone, you can use that. So you have like a knife, and then flip, and then just go to 1, 2, 3, like that. Don't do 10 times. You are not a professional. You are just going to ruin, Just 2, 3 times should be okay. If you don't have that, believe me, try it tonight. And then, your vegetable you can cut. But anyway, the grinding stone is more important here. So that's the stone, right? Grinding wheel is like a wheel, right? So then some grinder, have you ever used grinder? Okay, at least you saw. I mean, because I want you to know what I am talking about, because I don't know what DML, program is. That's why I don't know if they do grinding, But grinding stone is just a stone, but still abrasive. So, grinding stone, it's hard to draw because it's just wheel. Wheel, right? Something like that. And then you use this, abrasive and mixture. Then still you need more. Like, okay, I need smoother surface. Like I said, knee, right? 5 nano or less. You need that. And then you will use polishing, right? Right? So polishing wise, because I need this space, Polishing wise, what do you use? Like this equivalent to this cutter side. No. Reamer is similar to family of the turning. Honing is, yes. So honing is a process, right? So honing, polishing, even honing. Honing, yeah. And then something, this is a process, right? How about here? Yeah. So what do you use to do, polish as a cutter? Abrasive paste, slurry, so powder itself is okay, but abrasive or slurry means mixture of some dispersive media, could be water, could be oil, could be some polymer with abrasive. And then if it's coming to finer abrasive, you have some chemical additive because you have to have uniformly distribute abrasive, right? Otherwise agglomerated. When you make pancake, you put powder, milk, egg, or what? Salt, right? You mix, right? And then you see sometimes like agglomeration, right? Powder get, right? So if you have something like that and then you use for polishing, you have scratch. That's why abrasive has to be uniformly distributed. But abrasive means abrasive, abrasive means abrasive slurry. Slurry means abrasive plus some dispersive media. Could be oil or water or something, polymer, something, right? Media. Okay. And then abrasive paste. Okay, something like that, right? So these are traditional. Honing wise, just like, don't worry, I'm not going to delete it, but just like let's, because honing is one of the process, so then go like that, honing. So then, important is here. Now I'm going to use red, So then, turning and milling. You are controlling, you are creating shape and roughness, right? So turning and, like this, what do you control? Do you control depth of cut, you are trying to also transfer the like cutter edge geometry to the workpiece, right? So which means if cutter becomes dull, and then workpiece surface is going to be like, some sort of, periodical wave or something, right? Irregular things. And then grinding. Do you control depth of cut, right? How many micron you cut, right? And then you are not pushing, right? You are controlling the depth of cut. So this till here, you are controlling the motion. Motion means how much you are going to cut, and then how you are going to translate over the surface. Polishing. Did you brush your teeth this morning? I hope everybody did, right? And then this toothpaste, that can be abrasive paste. There can be some powder can be inside. Of course, it's healthy, don't worry. And then, do you control depth of cut? To your brush, like to teeth, how many micron your abrasive goes? Do you control? What do you control? Yes, force, right? Right, how much? And then also per, because it depends on the area. So this polishing, it's called pressure copying. So it depends on how much you press, then you control material removal. Right? Then outcome, you are controlling, okay, the geometry, form accuracy, and then surface roughness, right? Because you turn, and then, okay, you change the geometry, and then depends on how you feed, how you rotate the workpiece, and then you see the different surface roughness, right? Because rotation and then beyond, rotation, beyond, right? So this beyond means boyon, 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 right? Make sense? Right? You see that, and then if you do really nice mark, and then sometimes it's periodical cut mark, you saw sometimes rainbow, right? Workpiece. Do you know, like rainbow, like light reflection? If you have really, like a DVD type of things, if you go, right, so then you will have some, this is a chuck, right? And then you have a cut mark, something depends on how you cut, right? Something cut mark, right? And if it's really periodical, if you have light, then light reflect, right? If it's really good surface, you will see some rainbow, kind of, detection, your eyes. But the workpiece is not rainbow, right? Workpiece is silver, right? Something like that. So this, I said this, boyon, 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 right? That's, roughness, right? So you control both form accuracy, cylindricity, out of roundness, like these things, right? You control. How about the pressure copying process? When you brush your teeth, do you think you are copying your toothbrush shape to your teeth? When you wash your car, are you trying to copy your handle shape to your bonnet or car? No, right? Which means you are not controlling shape. You are controlling only surface roughness and then following the shape. And then you will claim, yeah, if I put the pressure too much, yes, you are going to change the condition, so that's different, right? And then also dwell time, if you want to remove more material, you will rub more, right? That's dwell time, staying there. But you are not controlling or copying your handle shape to workpiece. So you are controlling. So, this, okay, I'm going to go like that. And this is only the surface roughness. So I said this is super important. The reason is, this is a definition. So if you want to control, make some parts, unless you use motion copying process, you cannot control form accuracy, even if you try. Good luck. Because by definition, you cannot do that. And then as a matter of fact, yes, if you control dwell time and pressure, you will remove. So then, okay, you can control. That's how optics, final, optics like grinding, nice shape, and then go a little bit, right? But the lace, if you want to make some shape, you do, right? Or milling, you control shape, right? So anyway, this is the definition, and then I want you to remember, because you are taking my class, I think I can call myself, expert in machining, But this is important, because unless you understand this definition, you will never be successful. Okay? And then this one, we are going to start, like this one. So that's section 7.2, the single point, which means like turning, right? Only single point, single point tool operation. Right? Then I'm going to, turning, and then maybe, like a planing. Make it a flat one, planing, or even boring, like, you go inside and then go like that, boring, right? So, or even shaping or something like that. Because drilling, like two cutter, right? Usually, right? Twist drill, right? Milling, multiple cutter, right? That's a multi-point, cutting tool. But we will go from single point because it's simple. Okay? And then, step by step, we can study. So, figure, so 7.1 to 7.2. Right. So 7.1, it's just, only the chip. This is all the picture, and I will show you more modern things. But, so this is just, cutting. This is cutting insert, right? Insert is there, chip create. The top of the insert, that's the lake face, right? Remember? Have you ever heard of lake? Flank, right? You remember, right? Something like that. That's, you see the flank and then lake. And so that's, we will study from tool wear. I don't remember, Dr. Schuler, gave lecture. He talked about tool material, right? Right. So then we will skip that because he gave lecture, But anyway, this, cutting tool. And then turning wise, let's quickly, just review. I know you took already, DML, but even if, you are not like UF graduate, I'm sure you study, right? You study, right? Yeah. So then this is example of, cylindrical turning. And so this is, geometry, but also, quick terminology, right? So, we have this 3 tool. It's not at once, just case 1, 2, 3. And then this is workpiece. So then workpiece diameter D1 to now D2, right? Geometry, shape, you are controlling depth of cut. That's A, right? Depth of cut. And then this case, this, F, so T, I should go T1. T1 case, this is a tool, right? And then workpiece, rotate. Workpiece, rotate your side, right? I'm talking about your side, okay? In my case, go this way. But your case is go that way. Never use opposite, okay? So then chip comes from top. But here, chip thickness is H, right? And then B is chip width, okay? And then chip create from here. And then, this T2 case, it's similar, right? But they don't have this sigma, right? So this is, side cutting edge angle, maybe. Side cutting edge angle. So if you have sigma or not, and then go nothing wrong. It's just how you apply, right? And then this F both, that's a feed, right? Feed rate, feed. Then in this textbook, like now, like small lower, case n, that's a rotational speed. So and then now this case, just like I said, plunge cut or sectioning off, right? If you make like a groove, plunge cut. But if you go more, you can cut, right? Cut off. That's how this works, right? So then I think I've already talked about this B. So then chip width, and then this H, chip thickness, and then feed per revolution, and then this chip area. Okay, that chip area can be A times FR equal, like so again, and then B is the chip width, right? And then H chip thickness. I believe this drawing, So this is just kind of simple terminology and how turning works. Believe this, kind of reviewing, right? So then material removal rate, and also how we can estimate cutting force. Because when you cut something, our department prepare the machine tool which can cut your workpiece, right? But in general, you have to estimate, right? Like forming others too. How much force is required? How much power is required? Then you can choose which lathe, which machine you need to use, right? Otherwise, you try to cut, stuck. Because the machine doesn't have power, right? So that's why we have to study. So now, forming, okay, I shouldn't say forget about it, okay? So now we are studying about how to estimate. So even starting from turning, milling, drilling, and then I think that's the three, major things. And if we have time, we will do, grinding. And if we have more time, I'm happy to share laser machining or EDM, electro discharge machining, or other machining process, how it works. At least I can touch. But I don't know because of hurricane. We don't know. And then, because I say I have time to do that. So then, spring semester, I'm going to teach grad level. I'm going to teach entire this kind of only, no, I don't even touch this, what I'm going to study together with you, starting from ultrasonic. Then, go one by one, I can teach like rest of the, process, plasma and others, even ion beam, how it works, when you choose, how you can, differentiate. That's called non-traditional manufacturing, machining process. Okay? Then additive, also non-traditional, either subtractive or you're adding. But you did Lego. You already experienced additive manufacturing, right? You just don't think about it. But you are expert. Lathe, even fast cut, scissor. When you touch Lego, Duplo, when you touch scissor, which one you started? Earlier, faster. When you are 3 years old, 2 years old, Duplo, right? You are expert in additive manufacturing. I want you to know that, And then you are also expert in forming Play-Doh, right? You're expert, right? So actually cutting is the latest one. You have to study hard because you are not expert, right? Now motivation is there. Okay, so let's now background, you have enough, right? So okay, motivation, we are ready. So let's talk about the material removal rate, how we calculate. That's 7.2.1. We have to enjoy when we study, right? You can ask a question. That's a beauty. I'm from a different background. Professor didn't have office hours. We don't have even time of office hours. Professor, we don't talk. Professor doesn't, expect we say something. Right? Also, we didn't want to make a mistake, right? Professor just talked to this blackboard or chalkboard, you know. But now you are not. It's different time, you know. So you can ask. So I want to, you know, you to enjoy, you know, material removal rate. And then sometimes people, so even this textbook, you know, metal removal rate, because we are trying to just cut some metal, you know. But they use MRR, material removal rate. Okay? So the material removal rate, MRR. Q is a symbol, and they use Q equal A times B equal, I will explain BH, because this B or H, that's, you know, from figure 7.2, okay? And then equal A, FR, and B. And then unit for this one means this textbook, like cubic, you know, a centimeter, you know, per minute. But usually we do millimeter, right? Millimeter, and then, you know, like speed. Interestingly, you know, how did you use when we machine? Usually meter per minute. I mean, I don't use English, imperial unit. I'm using this metric, right? We don't say, you know, like meter per minute, you know, when machining we use in general. But anyway, you know, so I'm going to list what's A, B, something, but I don't have room here, so I'm going to change the page. But it's, again, you can find from figure 2. So what's A and B, because I have to list it. A, so, chip, because I expect we have equation, you know. Chip area, right? Remember that I had hatch, you know, in the, hatching on the figure 7.2. So that's, oh, sorry, millimeter. Then B, cutting speed. Then B, chip width. H, chip thickness. Then A, depth of cut. Then FR, this is feed per revolution. So I said like new, that's made by this. Feed per revolution. Right? So how many millimeter? And then sometimes the feed per revolution, people go like that too, you know, per revolution, REB, you know, the bottom, you know. But how many millimeter you move per revolution, you know. So then that's, you know. So we can use some, you know, exercise, you know, exercise 7.1, you know, a material removal rate in turning. Okay. So now we have a depth of cut, 6 millimeter. Feed, like feed per revolution, that's 0.25 millimeter. And then speed, 100 meter per minute. 100 per meter per minute, something, you know, very not like a titanium level, you know. It's maybe like easy for aluminum or something, you know, right? And then, okay, I think that's enough. And then what is Q, you know? And then Q, but unit-wise, you know, they are asking centimeter side, you know, so then cube, you know, per minute. I mean, exam-wise, I always specify the unit. And I'm not going to trick you, just usual, you know, like, you know, unit I will put. So if that's the case, and then we say Q equal, you know, A, FR, and then B, 6.25, 150. Again, this is a millimeter, right? and this is millimeter, and then this is meter per minute, then 225. Okay, that's it. So now you have this, material removal rate, and then how about cutting force? Right? So then turning. So the major principal force is like tangential, right? Because you have, in this case, you're like rotating, right? You have a tool here, then you cut, the chip goes like that. So this tangential force, that's why cutting force, the principal is Ft. That's equal Ks times A, or new things, Ks times A. What's Ks? This is equation 7.3. So this Ks, so that's specific force. Newton per square millimeter. So let's take a look at see table 7.1. Okay, so let's take a look at table 7.1. So that's next page, like 380. So let's take a look at that. Okay, this is 7.1, right? So then Ks value. Let's take a look at this one, Ks. So like carbon steel, now right, 1020, last 2 digit carbon, right? So if you increase the number, which means you have higher carbon content, it's more difficult to machine, right? So then Ks, you require more force, right? So that's why Ks increase. So something like that, and then some stainless steel even more, like 1045.45% carbon. That's quite high, right? And then this value, Newton per square millimeter. So then if you look at this right side, and then like this Inconel superalloy, right? So then you see 3500 compared to carbon steel 1020, 2100, right? So you get the idea, using this value. So this is, cutting force. This shows, the specific force, and then specific force times the chip area, right? So this is chip area here we talked about, right? So then that's coming here, right? Then you get, because of this one. So this, right? This can be here, and then this comes here, right? Then you get, cutting force. And then how about the power? Power equal cutting force, because that's a chip, right? Cutting direction. So times speed d. So then Ks times A B, right? And then AB, Q, right? So you can say Ks times Q, and then this can be what, right? Previously, the force is Newton, right? Newton, right? But now it's watt, so that's 7.4. Okay? Any questions? Just straightforward, right? So now, okay, fundamental is there, and then we are going to, study about more like a tool geometry. And I know it's 140. So next time, tool geometry, we will quickly look at the figure, 7.3. So I want you to take a look at 7.3. And then before the class, I uploaded some video for you. We will use for chapter 7 and 8. So I hope you enjoy some video machining, and then maybe you will just refresh your idea of machining. Okay, thank you so much.